Hello everyone, it's going to be lesson 2. It's going to be on quartic surfaces. Sometimes they're also called quadratic surfaces because they'll deal with like squareds and stuff like that. But before we do anything in the third dimension, R3, let's just look at some 2D examples, kind of jog our memory for what things look like in R2. So obviously, if you want to draw a circle of a radius r, that's a terrible circle, but I don't know, this is r, then all these points on the circle are all the points that are a distance r from the origin. So you could write that as a Pythagorean theorem pretty much. So you have this distance x, then you have this distance y. So you have to get this distance r, any point that's r away from the origin, you just write out x squared plus y squared equals r squared. Parabolas are pretty simple. If you want to do something like that, it's going to look like y equals kx squared. If you want to flip it, make it like that, just add a negative. We see a lot of parabolas, so I don't think we really need to revisit that. If you want to draw an ellipse, it's pretty similar to the equation for a circle, but it would differ in that you have ax squared plus by squared equals some constant squared. And in order to find these like important points, you would, so for instance, if I wanted to find this point right here and this point, that's when y is 0. So then I would have a squared x squared equals kx squared, or equals k squared, and then it would be x squared equals k squared over a squared. So those points are going to be k equals plus or minus k over a. And then y is just going to equal plus or minus k over b. So that's how you find those points. And then lastly, we want to look at hyperbolas, which could look like that, or they could look like that. Kind of like parabolas, but the equations are pretty different. They're going to take the form of x squared minus y squared equals k, or y squared minus x squared equals k, whatever you want to do. But essentially, if we said this guy took the form of x squared minus y squared equals k, this guy right here, and we wanted to find these points, well, how we would go about doing that is we would say that x is 0 at these points. So you would have negative y squared equals k. And then y squared equals negative k. So in order for this kind of, because you can't square something and get a negative value, that means k as a value itself must be a negative value, in which case you would get y squared equals negative the absolute value of k. And those would be those points. But if you, so now that we know that the value of k is a negative number, say it's like negative 3, for instance, right? I guess this would be easier to see. You'd have x squared minus y squared equals negative 3. And say we wanted to see where it intersects the x axis, we would say y is 0, so x squared equals negative 3. But there's no real values for x that suffice, that you could square to get negative 3. And that's why here we don't see it intersecting the x-axis, because there's no value that you could have it intersect the x-axis at. So I guess now if we move on to 3D space, probably the most relevant place to start is something like a sphere. So it's similar inspiration from a circle in R2, except instead of asking, oh, well, we're kind of asking the same question. What are all the points that are a distance r away from the origin? So we know that if we want to find a distance in R3, it's kind of an extension of the Pythagorean theorem. So say we wanted to find this guy right here. This was distance r. You would really just do x squared plus y squared plus z squared equals r squared. And you can prove this through just making a bunch of right triangles and then substituting. So it's really similar, except you just have this little z squared over here. And you would notice that when z is equal to 0, so in the xy plane, because that's when z is going to be equal to 0, you just have x squared plus y squared equals r squared, which is what we have in R2 for the equation of a circle. Also, if you just did if you wrote the equation out for x squared plus y squared equals r squared and plotted this out in R3, what you would get is, you would just get, here, I'll just draw a new plot. So say this is r. It's a circle all around. You're just going to get this. It's going to be going both ways. It's like a cylinder of sorts. It's going to be going up along the z-axis and down because there's no z in this equation, so you could plug in anything for z's domain and it won't really affect what this shape looks like. At z equals 5, say that's here, that's just going to look like x squared plus y squared equals r squared. At z equals negative 3,000, it's the same kind of thing. It's still going to look like this plot. Same goes for, now what if we drew out x squared plus z squared equals r squared? You could see that this plot, it's missing a z, so its center is going to be found on the z-axis, right, of these circles. So the center of this plot is going to be the y-axis. So if you drew them out, and then this was z, this was x, you could see that this gives you something like that in the xz plane, so this plane right here. And it'll just span out like this, and its center is just going to be the y-axis, similar to how the center of this is just the z-axis. So if you want a trace, for example, is what is like a cross section when one of the variables in the equation is 0. So I think a good way to kind of see this is, what if we were given this equation equals 16, right? And we didn't know that this was a sphere. How could we see that this is a sphere? So we would draw out our plot. So z, y, and x. And then we would draw in 2D cross sections. So we would say, okay, what if z is 0? So we'd have x squared plus y squared equals 16. Okay, and where is z equal to 0? Right at the origin. So that's going to give you the entire xy plane. That's when z is equal to 0. And then you're going to draw the circle out. So, I don't know, say this is 4. and this is also 4, you get a circle out like that. Sure, we could extend it out. Okay, now what about the YZ plane? What about when x is 0? So if we set x is 0, then you get y squared plus z squared equals 16. So then we already have this point where y is to 4. So this is a circle in the YZ plane. So it's going to look like that. But remember, x is 0. Okay, and then it's going to go down like that. And then under like that. That's a pretty poor drawing, but I imagine you get the idea. And then last step is, what about in the xz plane? So you got x squared plus z squared equals 16. So that this is just in this plane, you have this other circle. It goes like that. And it goes to -4, +4, and then also on the z-axis, this point right here is 4, and down here is at -4. Hopefully that gives you a picture of how, these kinds of curves kind of outline a sphere. Okay, now we could look at some more kinds of plots. What if we had x squared plus y squared minus z squared equals 0? So here you could simplify this. You could say x squared plus y squared equals z squared, and you could get to drawing your traces. So what if, let's see, if each of these, okay, if y is 0, then you would get, so if y is 0, you just have x squared equals z squared. So we need an xz plane. X is z. And this just means that x equals plus, or I guess you could, z equals plus or minus x, right? If you take the root of both sides. If z equals positive x, that's just this line. And if z equals negative x, that's just this line. So that's going to give you lines like that. And then stretch out our axes a bit more. You would get this kind of shape. If you did the same thing with the yz, you would get y equals plus or minus z, or z equals plus or minus y, and you'd get a very similar shape. Right? Now what if we did, this one's important, we can't x squared, when z is 0, it's just a point, x squared plus y squared is 0. But what if we treated x squared plus y squared equals a constant squared? Okay, so obviously this constant at k equals 0, which is just z equals 0, you're going to have just a point. Now, what if you grew this value? So what if you were at z equals 3? As this value grows, so if x squared plus y squared equals 3 squared, then you just get x squared plus y squared equals 9, okay? And this is at z equals 3. So if z was 3 right here, then you would have a circle of radius 3. Okay? And as this k value grows, you're going to get bigger and bigger circles, okay? And same goes for negative z values, because if you square negative z values, you're going to get a positive value here. So at -3, we would also have a circle of radius 9, or radius 3. And what this looks like is just a cone. It's a cone that goes like this, and it has these circular cross sections. It goes down to a little point, which is the z equals 0 point we looked at earlier, and then it grows again, like that. Okay. Now, what about a parabola? If you just had x squared or y equals x squared in 3D, that would just be, this is what it would look like. If this is the y, this is the x, z. So you would have a parabola like right here. But z is not here, so he's free in his domain. He can just extend up forever. And he's going to look like this. And obviously he's going to extend to both. Something like that. But what if we wanted like a 3D parabola? Oh yeah, this guy's just called a cone, by the way, this guy up here. A 3D parabola is going to be called a paraboloid. And he looks, he takes the equation of x squared plus y squared equals z. Because if you draw this out again, right, and you treated z as a constant, right, then at z equals 0, you just have a point, right, because x squared plus y squared equals 0. That's technically a circle of radius 0, and as that k value grows, you're going to get bigger and bigger circles, right? Along the z direction. As z grows, you get bigger and bigger circles. What about in the other planes? So let's say y is 0, you're going to get x squared equals z. That's just a parabola in the xz plane. So he's going to look kind of like this. He's growing like that. That's the negative x direction. That's the negative y direction. And then what about if x is 0? Then you're going to have y squared equals z. So that's just going to be parabolas in the yz plane. So it's going to be kind of tough to draw because I'm not really a very good artist. But it's kind of like that. You have these circular sections, and we could see this. We'll see this in Desmos at the end of the video as well. Now this one, this very last one, I'm not going to draw because it's complete pain in the ass, and I'm a terrible artist, as you could see. So, but I'm gonna describe it. So you have x squared minus y squared equals z. This is, well, first let's observe what this is gonna look like. So x squared equals z, that's just another parabola. Okay, I guess I'm gonna draw it. So, okay, now it's fine, but we'll label them. These are parabolas in the xz plane. And if x is 0, you have negative y squared equals z. So these are upside down parabolas. In yz plane. And then if z is 0, you have x squared equals y squared, which this is these are the crossing lines. So we have x equals plus minus y. So crossing lines in the xy. But these are just traces. The most important trace of these is when z is k, because when we have, let's write it out here, x squared minus y squared equals k, we get, this is the equation for a hyperbola. So we actually get hyperbolic cross sections as z changes, as this constant value changes. So you're going to have times when the cross sections look like this. You're going to have times when they look like this, and we'll be able to see that in the Desmos, which I have pulled up right here. Let me just type in the necessary equation. Okay. So this is what that looks like. And you could see that these, so at 0, they have the crossing lines that we found, this green line. And then this isn't moving up, but you could see that as it moves up, this hyperbola stretches further. I'm zooming out right now. This hyperbola stretches further. These vertices stretch further and further away from each other. We're pretty far away now, but you could see that. And then here, what other cross sections do we have? We have the y squared equals negative z squared. So y squared equals negative z. We have, that's one of our cross sections, remember. We also have this one, which is a parabola, an upside parabola in the xz plane, which we identified earlier. And then these are your hyperbolas that we found earlier as well. So this is called a hyperbolic paraboloid because you have parabolas, you have these hyperbolas. So what we used earlier, so for the paraboloid and the cones up here, when we observed that the trace isn't quite enough, we need this constant value to see as z changes, what do we get? So here we saw as z changes, we get these circles. Even down here with the paraboloid, we saw that as z grows, you get more circles. And z here can't be a negative value because you're squaring two numbers and you're adding them, so this can only be positive. So you cannot get a negative z value out of this, so it's only positive up here. But again here, we used a k value, wrong k value, but we used a plus y squared equals k, and this is z, and we see that when z is 0, we have just a point, and as z grows, as you go up, you get bigger and bigger circles. So observing these like cross sections at different values of a variable are known as level curves. They're curves that are at a certain level in the surface. So yeah, so now let's move on to 2 practice problems. If you did notice, this is only the first part of this lesson. There's actually 2 parts for quartic surfaces or quadratic surfaces, whatever you want to call them. So I couldn't get too many practice questions on these, but I did find 2. So let's take a look at them. So this first one's from Spring 2025, question 3 on exam 1. So it's telling you in planes parallel to and distinct from the xy plane, the traces of the quadric surface, this quadric surface, are what? So we could identify this. Earlier we saw that x squared minus y squared equals z. This gives us parabolas, this is a hyperbolic paraboloid. The only difference in this equation that they give us here is literally just this 4 right here, which you could rewrite it as this, right? So it's just scaled differently, but it's the same kind of outcome. So if we make a poor attempt to draw this out, we know that in the xz plane, you're going to have, but we are only concerned about planes parallel to. So what's a plane parallel to and distinct from the xy plane? It's any value of z. So this is like z equals some constant, right? But it wants it to be distinct from the xy plane. So not at z equals 0, because that's where we are at the xy plane, but it wants distinct from the xy plane. So not when z is 0. And then we could easily, that's a trap thing. If you didn't pay attention to this, maybe you would choose lines. Because when z is 0, you get x squared equals y squared. You get x equals plus minus y, and those are the crossing lines we saw earlier. So that's a trap answer. But what we do know is we have this x squared minus y squared equals k. And this is just the equation of a parabola. Of a hyperbola. Okay, we could ignore this 2 here because all it does, the only difference it makes from our standard equation is just scaling. It just scaled differently. And yeah, that is right. B is the right answer. I guess you would get, it wants parallel to and distinct from the xy plane. So in the xy plane, you only get hyperbolas. Parabolas you would get parabolas if you looked at the xz plane, remember? Or the yz plane, in which you would get the negative parabolas, which we saw earlier. So this is in the xz, and then this is in the yz. So, but it wants in the xy plane, so this is also a trap answer. Ellipses and circles, I'm not sure how you would get that. Isolated points, I'm not quite sure how you would get that either, but these 2 are most definitely traps. So, and we know that those aren't it because of this wording. Okay. The level curves of f of xy equals root of 36 minus 4x squared minus 9y squared are what? So remember, level curves are just like when you have a function and you want to look at its, so like you have some kind of x squared plus, I don't know, y squared plus z squared equals some constant squared. A trace is when you set one of these to 0 and you observe what the curve looks like at that point. A level curve is when you set this to a constant value and you observe how the curves change relative to how this constant changes. So this one's the level curves, not the trace. So f of xy, we see that this is missing a z, and z can be written as a function of x and y. So you have z equals root 36 minus 4x squared minus 9y squared. And you could rewrite this. Here, z is only positive, so that's going to affect what you're going to get out of this. Because when you simplify this, you're going to get 4x squared plus 9y squared plus z squared equals 36. Now, this is really similar to a circle or a sphere, but these values right here make it such that it's not a sphere, but ellipses, right? Because if you have something, and if we relate this to R2, if you have something that's in this form, right? And A is not equal to B, then you have an ellipse. So even at z equals 0, you have an ellipse. So that really eliminates everything but B. You could also ask, when are you going to get points? You're going to get points when z squared equals 36, because then you're going to get 4x squared plus 9y squared equals 0, right? When you're at z equals 6, you're going to get a point. You're just going to get a point because this is a circle or an ellipse of radius 0, and so you just have like a point. So these both are confirmed. You could really look at this in any kind of trace or level curves, and you're never going to get a parabola. You're going to only get 9y squared plus z squared equals 36. 4x squared plus z squared equals 36. And then we already saw it, but 4x squared plus 9y squared equals 36. And I know these are traces, and the question wants level curves, but we can do that here because this is just minus some constant squared. If we didn't treat it as 0, but a constant being squared, you just have that. And all that's doing is it's going to change how big the ellipses are respective to each of those axes. So if you looked at, let's take one of these and make an example of it. So take this right here. 9y squared plus z squared equals 36 minus k squared. So we know k is x in this scenario because this is missing an x. So when this is 0, you just have an ellipse that's gonna be it's gonna intercept z equals 6 plus or minus 6, something like that. And then for when z is 0, you're gonna have y squared equals 36 over 9. Root that, it's going to be 6 over 3, so 2. So something like that. And you have this. That's the trace. Now, as you change k, as k gets smaller, so as you move along this x-axis and k gets bigger and bigger, you're going to get 9y squared plus z squared equals some value c, where c is going to be less than 36, okay? And that just makes it such that this ellipse curves down to a value that's smaller and smaller until this expression is equal to 0. And that's going to be when k squared equals 36, when k equals 6, or when x is 6. So we know that at x equals 6, it's going to be 0 like that, and that applies to the back as well. So yeah, these have to be ellipses. Now, next lesson, you're going to get into some more complex, like it's pretty similar where you're looking at these curves and kind of judging how it's going to change as you change different values. But we're going to be looking at things like that are called hyperboloids, I guess, of 1 or 2 sheets. But that's for next lesson. Okay, thank you guys. Leave comments. Hopefully people are watching. And I'll see you guys tomorrow.